In the last lecture, we saw the definition of the Laplace transforms, and we saw that it is a special case of an integral transform. We also saw that it is defined using the concept of an improper Riemann integral, because the limits of integration for the Laplace transform is from 0 to infinity. So the ordinary Riemann integral can no longer be defined, and one uses a limit formula to define the so-called improper Riemann integral. So in this lecture, we will review the definition of the improper Riemann integral using limits, and we will also see examples where this limit may fail to exist, and so we should study the sufficient conditions under which these kinds of integrals are guaranteed to exist. So these limits will be finite. But before we do that, we will also see the sufficient conditions for ordinary Riemann integrals, and we will cover the definitions of what are called continuous and as well as piecewise continuous functions. And then after we have done that, we will see a sufficient two theorems on sufficient conditions for the existence of improper Riemann integrals. So in the last class, we saw the notion of an improper Riemann integral, and this was used to define an integral of the form ft dt from 0 to infinity, and this was by definition limit as r goes to infinity integral 0 to r ft dt. Now, first of all, for this definition to make sense, this integral within the limits, this integral between 0 to r ft dt must be finite, and then we say that the improper Riemann integral exists if the limit as r goes to infinity of this evaluation of this inner integral is also finite, right? So let me remind you that improper Riemann integral please edit out. So recall that the integral given in equation 1 in the definition 1 is said to exist if this limit on the right side on the RHS is finite. Okay. Now to see some examples and non-examples of this improper Riemann integral, let us take this following example, which we have already seen. First one is ft is e to the minus t. Now we have already computed this, and it turns out that first of all this so if you want to compute 0 to infinity ft dt, this is the limit as r goes to infinity 0 to r e to the minus t dt, and you get the limit r goes to infinity e to the minus r minus 1 by minus 1. Okay, and this final limit exists because the exponential function raised to a negative power will decrease as r goes to infinity to 0. So this is in fact 1. Okay. A second example where the integral exists is the following. So the following example, 1 over t to the power 3 by 2 3 by 2 defined in the domain 1 less than equal to t less than infinity. Okay. Now let us see this integral 1 to infinity ft dt exists as an improper Riemann integral or not. So we write it in the same way, 1 to r ft dt. So here note that the lower limit is not 0, is now equal to 1, but we are using the same definition for the improper Riemann integral. So in fact one can have any finite real number on the lower limit, and if the upper limit is positive in infinity, then we always take this definition as limit r goes to infinity with the integral from the lower limit to r. So it could be 1, it could be 0, the lower limit can be 1, it could be 0, it could be any other finite real number. So in this case the lower limit is 1. Now let us see if this integral exists. So we integrate t to the power 3 by 2. So we can evaluate this integral 1 to r dt by t to the power 3 by 2, and you get limit as r tends to infinity minus t to the power minus half, okay, and this is from 1 to r. So in the end you get limit r goes to infinity 1 minus 1 by square root of r. Okay. Now again this 1 over square root of r term as r goes to infinity goes to 0. Goes to 0 as r goes to infinity. Therefore in the limit you simply get 1. So the integral 1 to infinity ft dt, where ft is 1 by t to the power 3 by 2, is in fact finite, and it exists as an improper Riemann integral. Now let us see an example where the improper Riemann integral does not exist. Okay. So the easiest example is ft equals t greater than equal to 0, and if you take the integral 0 to infinity ft dt, then you, by definition this is again limit r tends to infinity 0 to r ft dt, which is again 0 to r t dt, and you get simply t square by 2 0 to r. So you get the limit r goes to infinity r square by 2, but now this goes to infinity as r goes to infinity. So in fact this limit is now not finite, and therefore this improper integral, this improper Riemann integral does not exist. Integral does not exist just because this is not a finite. Another example is ft equals sin t for t greater than equal to 0. So if you compute 0 to infinity sin t dt, this is limit r goes to infinity 0 to r sin t dt, but this is limit r goes to infinity, you will get 1 minus cos r. But here in the second term, this cos of r term does not converge to any finite limit as r goes to infinity, because the cos function will oscillate between -1 and 1 infinitely often as you take r to infinity. So this limit does not exist. This limit also does not exist, And so we also say that this improper Riemann integral of ft equal to sin t does not exist. So we have seen that improper Riemann integrals may or may not exist. Now it will be useful to have some sufficient conditions which will guarantee the existence of such improper Riemann integrals, and so this is what we will study now. So these are sufficient conditions for existence of improper Riemann integrals. First of all, before talking about sufficient conditions for existence of improper Riemann integrals, let us see a sufficient condition for existence of ordinary Riemann integrals. By an ordinary Riemann integral, I mean an integral of the form a to b ft dt, where a and b are finite values. Okay, so without loss of generality, I am taking a to be positive. You can also have a negative, but since all our computations will be on the positive real line, I am here taking a to be positive. So this is a theorem which gives the sufficient condition for the existence of ordinary Riemann integrals. This is that if ft is a continuous function on the interval ab, on the closed interval ab, then this integral a to b ft dt exists, meaning that this is a finite value. So recall the definition of a continuous function. So a function f which takes real values is called continuous if for every point c in this interval ab. So first of all, let's take it in the open interval ab. We have, first is that fc exists. Again, exists means it is finite. And secondly, limit as x tends to c plus fx exists. Third, limit of x tends to c minus fx exists. And lastly, fourth condition is that these two limits are the same, that the limit as x tends to c from the left side, c minus, is the same as x tends to c plus. So this is the limit as x tends to c from the right side, and this is equal to f of c. So we see that these four conditions give you a continuous function. So graphically, let me draw a picture. So this is x, this is fx, y equal to fx. So let me draw a picture. Now suppose that here is your A, here is your B, and you are considering some point C in between, and your function looks something like this. Okay, so this is y equal to fx. Now at C we have this value f of c. Okay, now the second condition says that limit x tends to c plus fx exists, which means that when you approach c from the right hand side, from values greater than c, then the corresponding limit as you traverse this graph of fx also exists. And the third condition says that the limit as x tends to c minus, meaning that x tends to c from below, from the left hand side, then again your limit as x tends to c minus fx exists. And the fourth condition says that all these three values are the same. Okay, so this means that informally, if you take a pen and you move your pen over the graph of fx, you can move your pen without taking it out of the paper. Okay, this is an informal definition of a continuous function. So what won't be a continuous function? Maybe that's something we should need to see to understand continuity. So let's say A and B are here, C is here, and our fx looks something like this. So our fx looks something like this. So here is our line x equal to c. Now let's see which part is getting violated. So here I am assuming that this is fc. So in this graph we have that when you approach fc from c from the left hand side, you get this value fc here, but when you approach c from the right hand side, you get this value here. Okay, therefore these two values do not coincide, and so there is a discontinuity at the point c. Okay, so this is about the definition of continuity at an interior point in this closed interval AB. In addition, we should also say what happens at the endpoints A and B. So let me write the fifth condition, which is the limit as x tends to b minus fx exists and equals fb, and the sixth condition is that the limit of x tends to a plus fx exists and equals fa. So all these six conditions together make a continuous function on the interval AB. So note here that when you are talking about the upper endpoint, then you are approaching from the left here, and when you are talking about the lower endpoint A, you are approaching from the right. So here you are approaching from the right, and here you are approaching from the left. Wherever the function is defined, you can only approach from that side. So this is how a continuous function is defined. So our theorem says that if this function is continuous on this entire interval AB, closed interval, then this Riemann integral, ordinary Riemann integral ft from a to b dt, this will exist.